To recording. Okay. Yeah, so I don't think I have any announcements for today. The test is on Friday, and that'll be chapters 5 and then 6, 7, and 8. So last Friday and then this week. Um, Today we're going to be covering chemical reactions. So yesterday, I mean, your head might still be reeling from yesterday's lecture and naming everything. That was it's a lot. It's a lot to cover. Or chemical, yeah, composition, molecular formulas, all that. And now we're going to be applying that to chemical reactions. First, today we're going to go over all the different types of chemical reactions. There are a bunch of them. Yes, there are a lot of different types of chemical reactions. So we're gonna cover those. We're gonna talk about those. We're gonna talk briefly about oxidation reduction reactions today, and then there's a little bit more that we need to do. Tomorrow's chapter 8 lecture should be pretty short. And there's a little bit more that we need to do about
Does that
reduction
make
reactions before that.
chapter 8 super easy?
What was chapter 8 exactly? Oh, quantities in chemical reactions. So, right, we talked about how basically we've talked about converting between moles, what a mole is, atoms, like, those kind of conversions is what we did yesterday, right? Empirical formula, that kind of thing. Today we're going to talk about what the reactions are. Whoops, my microphone. So we've got, there's combustion reactions, there's double replacement reactions, oxidation reduction reactions, and then tomorrow what we're going to talk about is how do we then apply quantities to those to say, this much of X reacted with this much of Y, and that creates how much of, W and Z, right? So that's sort of the steps that we're taking here towards that end. So today is not going to be so much calculation heavy as it is going to be, again, classifying things, right? That's sort of the overarching thing for general chemistry is how do we take these chemical concepts and group things together. And if you can group things together, then you can do the math to solve for different quantities. And that math ends up being a lot of the same from thing to thing, but putting together those reactions and properly predicting what the products are going to be is sort of the key to it. So we're going to talk about that today. You might be familiar then. Sorry. One more note about the exam on Friday. I'm giving you obviously you'll get more time for the exam because there are a lot of people who ran out of time. So you're going to get more time. You're also going to get more time to take the exam. So if you wanted to, the exam is available from Friday at noon until Saturday at 6 p.m. So you can take all day Friday to study if you want, and then you still have pretty much all day Saturday to take the exam at some point. Probably going to be aiming for around 50 questions, and I'll probably give you something like 110 minutes to take the test. So right before you had just over a minute per question, this time you'll have roughly 2 minutes per question. And a lot of it is going to be, right, what kind of reaction is this? There will be, of course, calculating some quantities, which we'll cover tomorrow. There's going to be compound naming stuff on there, right? Is this an ionic, molecular, compound? Really, I mean, it's everything that we're covering here. So, are there any other questions about that before we get going? All right. So when we talk about chemical reactions, we're talking about the transformation of one or more substances into different substances, right? So we're taking our molecules, combining them with other molecules, or atoms and combining them with other atoms, rearranging them to get new products. The one that a lot of people are familiar with is the baking soda volcano, where you add baking soda and vinegar inside of a paper mache volcano, usually a little red food coloring. This creates a lot of CO2 gas, water, and sodium acetate. And you add soap in there too as a surfactant, so you get lots of bubbles. So the carbon dioxide bubbles out of the mixture, the carbon dioxide bubbles out of the mixture, causing the eruption, right? So it creates a whole lot of volume and forces all of the foam out of the top of the volcano. So reactions that occur in liquids and form gases are gas evolution reactions. So we're evolving gas out of the liquid. In our cars every day, and in an automobile engine, right? It's an internal combustion engine. It's a combustion reaction. And we're taking hydrocarbons like octane, right? That's the octane rating that you get on your gas. From gasoline combined with oxygen to form, with oxygen from the air, we react those together to form carbon dioxide and water. And that also releases a lot of heat. And that heat causes pressure, which pushes your pistons, and gives us the internal combustion engine. But combustion reactions are a subcategory of oxidation reduction reactions, in which electrons are transferred from one substance to another. And again, we'll definitely get more in depth on these as we go on. Sort of another common reaction, something that you kind of see every day, is laundry detergent. And actually, you don't see this, I suppose, but laundry detergent works better than hand soap. You can't just fill your, washing machine with hand soap, because laundry detergent actually contains substances that soften hard water. So hard water, especially here in the valley, contains lots of calcium and magnesium ions, and those interfere with the action of the soap. So they react with the soap, and they form this gray, slimy, scuzzy substance called curd or soap scum. So when you put soap in pure water, you can see here we have soap in pure water. Looks really clear, but then you've got this gray, gross-looking, sick-looking color for the soap in hard water. And so your laundry detergent then has sodium carbonate in it. And that carbonate, when you dissolve sodium carbonate, you get carbonate ions, which will react with your calcium and magnesium in the hard water to form solid calcium carbonate or magnesium carbonate. Those solids then are not soluble in water, and they fall to the bottom of the laundry mixture. And that removes those ions from the water, so you get better action out of the soap for cleaning your clothes. Reactions that form solid substances in water are precipitation reactions. So we talked about oxidation reduction in your combustion engine, right, in your automobile. We've talked about precipitation reactions now here with the soap, and then gas evolution reactions, and these are just three sort of examples of those. So if you remember back to when we talked about physical and chemical changes, we can often see if something is a chemical change based on how the properties change. And it would be really, really easy if you could see atoms and molecules, because we've got atoms combining with other atoms to form compounds. Our starting molecules can decompose, so they can break apart. We can form new molecules. Or atoms in one molecule changes with atoms in another. They swap spots. But we can't see them, so we have other ways of identifying when a chemical reaction is taking place. One of those is a color change. And I know we talked about color as a physical property, but changing color is a chemical change. So what's happening actually in this spoon is when the molecules that cause that red color in the spoon are exposed to high heat, the shape of the molecule actually changes, and they reconfigure to be this white color. And as soon as you pull it out of the spoon, you pull the spoon out of the hot water, those atoms will go back to their original configuration and be red again. So that's that would be a reversible chemical reaction. Formation of a solid is a dead giveaway in terms of seeing a chemical reaction. If you see precipitation, that means you have some sort of chemical reaction going on. Now, you got to be careful too, though, because sometimes you'll add. This would be coming from adding one liquid to another liquid. So a solid forms in a previously clear solution. Sometimes when you mix two liquids, though, they'll be cloudy for a little bit until they finish mixing. And so you got to be careful that precipitation persists. This is maybe not so familiar anymore, but Alka-Seltzer, right? So if you drop Alka-Seltzer tablet into water, it results in a gas evolution reaction. This is different than adding Mentos to your soda. So adding Mentos to soda is not a chemical reaction. Instead, what's happening there is the Mentos actually is not perfectly smooth, but it's got a bunch of little dimples in it. And those dimples, because the carbon dioxide in your soda is not coming out as the result of a chemical reaction, it's coming out because basically at the factory they forced too much CO2 into the liquid. And so that CO2 doesn't want to stay in the liquid, and if you give it something to stick to and form bubbles on, those rapidly will leave the solution. Whereas with the Alka-Seltzer, there's actually a chemical reaction happening there that's converting that tablet, parts of that tablet at least, into gas. Often heat absorption or emission and light emission, those are results of chemical reactions. So right, we burn natural gas on your stove if you're lucky enough to have a gas stove. Still really wish I had one someday. Or if you have a lighter, right, you're burning that gas or butane, and that's creating heat and light, chemical reaction. For a chemical cold pack, there's a barrier in that cold pack. When broken, the substances mix, and there's a reaction that happens there. I don't know if we're going to get into it in this class. I know on the lab 1, there was, I know my dad mentioned when he mixed two of the solutions that it got a little bit cold. That's not necessarily a chemical reaction. That one, as many of you noted, was not a chemical reaction. The process of mixing can require energy, and that can cool. But mixing or dissolving are not chemical processes. So, and then glow sticks. Huh?
That was a trick, seemed like.
It was a trick. I don't know why he mentioned it.
The cold pack, when you're mixing two substances, get cold. So that's the fact that it's getting cold is the evidence of a chemical reaction. But in that lab, I put a chemical reaction because I thought, oh, well, it's getting cold. It'll be a chemical reaction.
Yeah. When I watched the video, I was like, I shouldn't have mentioned that. Because, right, yeah, you can, in something like a chemical cold pack, there's a chemical reaction happening, but sometimes you mix solutions and they get a little bit cold. Yeah, I think it'll be pretty clear. I mean, obviously I'm writing the exam, so I'm not going to put in a question that's like that. I'm not going to say, if I do, it'll be like a cold pack, right? So like a cold pack, or, I'll try to make it more clear. I don't want that to be a tricky question. So, not evidence of a chemical reaction. We can be fooled, right? So when water boils, we're forming a gas. But that gas is water converting from liquid water into steam. And there are also chemical reactions that can happen without any obvious sign. So you could mix two things together. They could be reacting. There could be no temperature change and no color change, but they've reacted. So this is why you need to have an understanding of the basis of what's going on. And why you need to understand that, like, water boiling is not, or like a soda, right? When you open up your, this is actually soda. I ran out of cups. But when you have a soda, like, that gas coming out of the soda is not a chemical reaction. It's just CO2 trapped in the liquid. And so it is, in the same way that you would boil water, CO2 is a gas at room temperature. So it's going from that liquid to the gas. So for the skill builder, we'll talk about, let's say, so which of these are a chemical reaction, right? So butane burning in a butane lighter. And I want to highlight two here, right? Keywords. So burning. Burning is always chemical. Butane evaporating out of a butane lighter. And again, the key word here, right, is it's evaporating. Evaporation is a physical process. Burning again, right? Wood burning. Whoops, I almost wrote physical. Chemical process. And then dry ice subliming. That's maybe not as common a word as evaporating or burning, but subliming means going from a solid to a gas, skipping the liquid phase. And so that is then a physical process. Right? Because whenever you burn something, you're changing it from whatever it is, you're adding oxygen and converting it into really CO2 and water. And we'll do a bunch of those later. But for evaporating or subliming or boiling or freezing, those are all the same. It's the same compound. It's just in a different physical state. So when we write chemical reactions, we write them as one of these chemical equations. And so we have our substances on the left side that are our reactants. And then we have our substances on the right side, which are our products. Right? So we're reacting these two things together to produce the ones on the right side. And it reads just from left to right, like you would read a sentence. And then this came up before too, but we mentioned, or we write in here the physical state of each of these in parentheses or as a extra little subscript to the bottom right. I probably won't always write them in parentheses, but it is helpful to write them in parentheses because then it sets it apart from your subscripts. All right, so these are the abbreviations, and this one came up before too. Aqueous, which just means it's a water solution. So it's something dissolved in water or something that's miscible in water. And then just gas, G, liquid, L, S, solid, right? So aqueous is probably the only one that you have to remember there. Um, so then the left side of our chemical, so okay, here, yeah. When we're doing these chemical reactions, right, we're really just taking whatever atoms we have on the left side have to all be on the right side, but they'll probably be they should be rearranged if they're reacting. So if something is on the left side, it has to occur on the right side. So you can see here we have these space-filling models of our different molecules, right? So we have CH3, CH4, right? So there's, well, they're talking about the oxygen atoms here, but if we have one carbon and we have 4 hydrogens, right? And then we have 2 oxygen atoms. These oxygen atoms, right, are just being moved over here. Is this balanced? Oh, this isn't balanced. So we need to balance this, right? Because we have 2 oxygen atoms, but then we have 3 oxygen atoms on this right side. So we can't simply create this extra oxygen atom out of nothing. It has to come from somewhere. And so that's what we call balancing a chemical equation. So to balance this equation, we change, I think this is the next slide. Yeah, so we have to create a balanced chemical equation. Oh, right. So now we're talking about hydrogens, right? So we have 4 hydrogen atoms. We have 2 hydrogen atoms, right? So this is not a balanced chemical equation. So we've got, right, a mismatch in our oxygen, and we have a mismatch in our hydrogen. So to fix that, what we do is we add coefficients. We add these numbers in front of the molecule's molecular formula to change the number of atoms really on either side, right? So now we got 4 hydrogens over here, and we have 4 oxygens, right? Because 2 times O2 gives us 4. Sorry. And then on the right side now, we have 1, 2, 3, 4 oxygens. And then we have I should do this in a different color. 1, 2, 3, 4 hydrogens. And you don't need to write out space filling models, right? You can see that here we have 2 times 2 hydrogens, so that's 4 hydrogens, which matches up with these ones over here. And we have 2 times 2 oxygens on the left side, which matches up with the 2 oxygens here, and then 2 times 1 oxygen, so then we get 2 oxygens there. And then 1 carbon on either side. So when we balance these chemical equations, there's steps that you can follow that will help you balance it every time without having to iterate or try a lot of different things over and over again. So you start first, you write out a skeletal equation by writing the correct chemical formulas for each of the reactants and products. And so you can go back to chapter 5 and review those nomenclature rules if it gives them to you in like a written out form. If an element occurs in only one compound on both sides of the equation, you balance that one first. If there is more than one such element, you balance metals before nonmetals. And we'll go through a bunch of examples of this. And then if an element occurs as a free element on either side of the chemical equation, balance it last, right? That's easy to balance. It's on its own. If you change the coefficient there, you're not going to change the coefficient for another element that you're going to have to then change later. So you always balance free elements by adjusting the coefficient on the free element, right? Because if we change the subscript will change. By changing the subscript, you change the identity of the molecule. So we only change coefficients. If the balanced equation contains coefficient fractions, you change these into whole numbers by multiplying the entire equation by the appropriate factor, right? So if you ended up with somehow a half or a quarter or a third, then you multiply, right, by 2 or 4 or 3 to get whole numbers. Then you want to check to make certain the equation is balanced by summing the total number of each type of atom on both sides of the equation, right? So you write out a little table, say carbons, oxygens, hydrogens, irons, whatever is present on the left side, count all of those up, and then do the same for the right side, and they have to match. So you do change the coefficient, do not change the subscripts. All right, now we'll do some examples here. So we have solid chromium oxide and solid carbon to produce solid chromium and carbon dioxide gas. So first, you got to look up where chromium is and what chromium's symbol is, and I'm just going to kind of go quickly through these because there's a lot to get through. So we have chromium, which is Cr, right? And it's a Cr3+, which we know from the Roman numerals here. And we know oxide is just oxygen, and that's going to be a 2-. So if you do your crisscross rule, right, we're going to get 2 chromiums and 3 oxygens. And that's a solid, so we'll write down solid. And then you're going to put a plus here, because we're combining these things. Leave space for a coefficient, in case you need one. And then we just have carbon, solid carbon, right? So then we'll put solid. And then for our products, a good rule of thumb is to write down your cations first, or your the front part of the molecule, right? So we're going to do, since we only have one, we'll do chromium first. So again, leave space for a coefficient. Cr. Oops. And we're going to have chromium. We're going to get solid chromium and carbon dioxide gas. So Cr is going to be by itself. I guess in this example they tell us exactly what we're going to get. Leave a space for a coefficient. Carbon, right, dioxide, gas. Okay, so now we've written out our chemical equation, our skeletal chemical equation, and we need to balance this. Or we should check to see if we need to balance it, right? So we have our first step, we'll just go back to this. Right, our first step is to write a skeletal. Our second step then is if an element occurs in only one compound on both sides of the equation, balance it first. If there are more than one such element, balance metals before nonmetals. So let's go back over here, right? We have chromium.
Can I ask a quick, is
Yeah.
that going to change your results if you do it out of order, or is it just making it easier to follow that order?
It just makes it easier to follow that order. No, so if you do this right, you're not going to get a different result. Or sorry, if you balance it properly, it does not matter really what order you go in. But in general, if you do it according to these steps, you'll get there faster. So I guess we'll do it properly first. Because if I change, well, I guess I'm going to start left to right here. Because it says if we have something in only one element, or that occurs in only one compound on either side, balance that first, right? But we have chromium. Let me erase this. Right, so we have two of those though. We have chromium, which only occurs in one compound on the left side, but we also have carbon, which also occurs in only one compound, and that's on the right side. So since there's a tie, we balance the metal first. So we'll do chromium. So we see over here on the left we have 2 chromiums. On the right we only have 1. So we can just add a 2 in front of that. Right, so now we've balanced our chromiums. And then we're going to move to the other compound that's in a single, occurs in a single molecule. Right, so carbon. So say carbon's actually balanced on both sides. And then we'll just move to whatever, or actually, what is the next rule? If an element occurs as a free element, we'll balance those last, okay? If the balanced equation contains any coefficient fractions, do we miss something? So I've actually never used these rules before.
Doesn't look like it's going to balance.
It's not going to balance very nicely. And this is where it is in some ways just intuitive, right? So you remember the crisscross rule? I'm actually going to erase this. So the crisscross rule, right? So we have 3 oxygens on the left side. We have 2 oxygens on the right side. So to get those to balance, we're going to have to go 3 and 2. Oh, I think I know what I did. We shouldn't have balanced chromium because chromium exists by itself on the right side. So we wanted to balance oxygen first, because chromium and carbon both have these sort of free elements here, but they're sort of freestanding. So by changing the coefficients on chromium here or carbon here, we don't change anything else, right? So if we do oxygen, that's changing the number of carbons when we add a coefficient here, and that's changing the number of chromiums by changing the coefficient here. So now we can go back and say, okay, we have 4 chromiums on this side. We only have 1 on the right side. But we can add a 4 here, and now the chromium is balanced. And then on the right side, we can say we have 3 carbons, and we have 1 on the left side, but we can just add a 3, and that balances. So now if we go back and look at either side, 3 carbons, 6 oxygens. And then since I have carbon here already, right, we know that's balanced, but then we can do 4 chromiums and 6 oxygens. So we're balanced. We got a lot of these though, so we got a lot of examples. Okay, so now we're working with writing a balanced chemical equation for the combustion of gaseous C4H10, which is butane, and gaseous oxygen to form gaseous carbon dioxide and gaseous water. So,
Yeah, it's gaseous water still H2O,
yes.
right? Okay,
Yeah, right. So if you boil water, it's still water, it's just in a gas form.
cool.
So then we'll just start with C4H10. H10 plus, right, leave a space for your coefficient. Gaseous oxygen, and this is where you need to remember your Brinkelhoff compounds, because gaseous oxygen is O2. Oh, I forgot to write G. I do want you to write that out and include that when you do these in, maybe not the homeworks. You should do it in the homeworks, but also in things like the labs or worksheets. I will be grading for those. Right, and so then we're going to form carbon dioxide, CO2, carbon dioxide, 2 oxygens. Again, a gas. And then water, which is one of those where you just have to remember the common name for it. So again here, now it's a little bit easier since we have, okay, so we know oxygen, right? We have this freestanding oxygen. So we don't balance oxygen until the end. So we can start with either carbon or hydrogen. Let's just start with carbon because it's first. So we have 4 carbons on the left side, and we have 1 on the right side. So we'll go ahead and say we have 4 carbons there, right? Changing the coefficient, never subscripts. And then we have C4H10, so we have 10 hydrogens. So we add a 5 to the front of H2O, right? Because we have H2, so now we have 10 hydrogens. Now we'll count the number of oxygens that we have on the right side. So we have 8 oxygens here, and we have 5 oxygens here. And that's going to give us 13 oxygens. But we have O2. So it looks like we're going to have to multiply here, right? So this is not going to be, we need half of 13. There's going to be 6.5 or 6.5. Right, see how that works? Because now we have 13. So we're balanced, but according to that last step, we now need to multiply everything by a coefficient in order to get whole numbers. So I'll go ahead and write those down in red over here. And so we're going to multiply, since we have a half, we multiply by 2. And so we're going to get 2 C4H10. We're going to have 13 O2. We're going to have 8 CO2, and we're going to have 10 H2Os. So 2 C4H10 gas, 13 O2s gas, 8 CO2 gas plus 10 H2O gas. And that would be your balanced chemical equation, or chemical reaction. Either one. So just to double check, right, we can say, okay, we have, let's do carbon. Let's balance them in this order. Carbon, hydrogen, oxygen. Carbon, hydrogen, oxygen. or we'll check the numbers, right? So we have 8 carbons. On the right, we have 8 carbons. We do our hydrogens. We have 20 hydrogens. And on the right, we also have, right, 10 times 2, 20 hydrogens. And then if we look at oxygen last, 13 times 2, 26. And then we have 16, and we have 10 oxygens, right? So we have 26. And you can see that our chemical equation is balanced.
Can you show me again real quick how I got that 6.5?
Yes. So we did... right before we balance, we have on the right side here, I should pick a different, I need to get a different color going here too. Ooh, let's use this one. Right, so we had, before balancing, we had the 4 times 2 oxygens, right, so 8. And then we had 5 times 1, which gave us 13 oxygens. And then because this is O2, right? So we're going to multiply whatever coefficient we have by 2. So what we do then is we take the 13 and we divide by 2 to get 6.5 O2. Good?
Yeah, thank you.
Okay. Leave that for a second longer. Save that new color as a favorite. Oh, it broke my favorite bar. Hold on. Nope. Okay, well, we'll continue on. So let's write a balanced chemical equation then. So now we have, this is another problem where you're going to have to, right, know your nomenclature. And there will be questions like this on the test, where you need to know what the nomenclature is in order to write out your chemical reaction in the first place. So lead, right, so we have lead. Acetate. Acetate is one that you'll probably have to look up. Acetate actually is often abbreviated AC minus, and then acetic acid is HAC. Acetic acid is also vinegar. I'm not sure if that's in the book as one to just kind of memorize. I'll double check that if I use that as a question. The chemical formula for, or the molecular formula for acetate is also C2H3O2 minus. Right, so it's a polyatomic anion. All right, but we have lead acetate. We know that lead has a 2 charge on it. So we're going to say lead, and I'm going to abbreviate acetate here. So we're going to say lead, AC. Oh, actually, I'll just write it out. We'll do C2H3O2, because then we can practice, right? This needs to be in parentheses. There's 2 of those. And then we're going to have aqueous. Oh. All right, we have aqueous lead. Wonderful aqueous lead. It'll make your water sweet, but it will also poison your brain. So potassium iodide, aqueous potassium iodide, right? So we know potassium is a 1A compound, so it has a +1 charge. And iodide, or iodine, is in the 7A, so it has a -1 charge. So we get Ki. And we'll do aqueous, right? And then we're going to form solid lead iodide. Coefficients base. And remember, iodide has a -1 charge, and lead has a 2+ charge. So we're going to get lead iodide, 2 of those. And then we'll end up with aqueous potassium acetate. This is just too much to write. Actually, this is, okay, so we need space for a coefficient in case we need it. And then potassium. Then we're going to do C2H3O2. We don't have to add parentheses there because we only have one of them, because acetate has a -1 charge. Now I'm going to take this whole thing and a little iPad magic to shrink it. So again, you can sort of do these intuitively and just start throwing coefficients in and start balancing things and try and figure it out as you go. You can also kind of follow the steps. So do we have anything that exists only in one compound? Lead is only in one compound on the left and right. Switch to this other, right? Lead is only here and here. Potassium also only in one on the left and right. So shouldn't matter which one we start with, but we know that lead and potassium actually are both already balanced, right? So we have 1 lead on the left, we have 1 lead on the right, 1 potassium, 1 potassium. So instead we can move either to the acetate or the iodine. So if we just go to, let's do the acetate first because it comes first. At some point you just have to make decisions like that. So we see that we have lead, we need 2 acetates. We have 2 acetates on the left side, so we need 1 more on the right side. So we add 2 coefficient. And that's also something to note too, right? We don't need to balance carbon, hydrogen, and oxygen separately in this equation because we know they're a polyatomic anion. They will move together as a group in any reaction. So things like nitrate, sulfate, phosphate, iodate, these polyatomic anions move as groups, so you can balance them as groups. Right, okay, so now we've balanced our acetates. Now we see that we actually have to change the coefficient for potassium, because now we have, update these as you go. Now we have 2 potassium, and so we can look over to the left side and see that we have potassium iodide, and we can balance that one. And so then we'll go, right, we need 2 potassiums, so we'll put a 2 there. And you'll notice that we have now automatically balanced our iodine. So the way that these problems work out usually, you can get stuck in a loop. So if you start balancing one thing and it changes another thing, and then you come back and change the initial thing, and you notice that your numbers keep going up and up and up, you're stuck in a loop, and you should reset and start by balancing a different element. So now we should check and make sure that we have the same number on both sides. I'll use a different color again for this. So we have 1 lead, 1 lead. We have 2 acetates, C2H3O2 minus. We have 2 potassiums, and we have 2 iodines. And then on the right side of the equation, we have 1 lead. We have, and we'll do these in order, right, so that they match up. So we'll do, not potassium, but C2H3O2. And we have 2 of those, right, because coefficient times that, 2. Then potassium, same thing, also being multiplied by 2. So we have 2 potassiums. And then because of the subscript, multiplied by 1, so no coefficient, right, is implied as 1, then we have 2 iodines. And we can see that we've balanced the chemical equation. Keep on going. So you won't always have to write out the entire equation. Sometimes you'll be given part of the equation. So again, we want to see if we have any compounds that are part of only one on either side of the equation. So we have hydrogen. That's a great place to start. Do we have anything else? Chlorine is in this molecule on the left, but it's by itself on the right. Oxygen is by itself, but it's part of hydrogen on the other side. So because hydrogen is part of HCl and it's part of H2O, we'll balance that first. So we have 1 hydrogen on the left and 2 hydrogens on the right. So 2. And then that balances. Then we'll move to chlorine. Do chlorine next, and we see that chlorine actually, because it has this this subscript, and on the left we have this coefficient. So we have 2 chlorines on either side. Then we can move to oxygen. We have 2 oxygens on the left, and we have 1 oxygen on the right. So then we can see that we need to balance oxygen. So if we balance oxygen here, we're going to go from H2O, so we have 1 oxygen, but we need 2. So we do 2 here. But now we've changed the number of hydrogens. We'll do it this way, and then I'll show you a trick. So we have 2 oxygens now, our oxygens are balanced, but now we've changed the number of hydrogens. We need 4 hydrogens. So now we have 4 hydrogens on the right. So we can come back and change that. Now we have 4. Now we need to change the number of chlorine. And so we'll change the number of chlorines because we need 4. Cl is a Brinkelhoff. So it is a diatomic. So there's 2 chlorines there. So we just multiply this by 2. So the shortcut then, if I can just do below here, when we got to this point and we had 2 HCl, O2, right, and then we had H2O plus Cl2, we can see that we have this where we have 2 and we have 1 on the right side. So the other thing you could do here, instead of adding the 2 like we did and then coming back and changing the hydrogens, I guess we'll still have to do that this way, but you can say, oh, well, I need half of this oxygen to match the oxygen number that's on the right side. And then you multiply everything by 2 because we have a half, and so then we'll end up with the same result, right? So 4, this will multiply by 2 to be 1, and these will be 2 and 2. Here's an example of, there are multiple ways to do these, to balance these chemical equations.
I like that trick.
Yeah, can make it a little more clear, especially when you've got these things like Cl2 and O2 when it's by itself. All right. So we've mentioned aqueous solutions as being, something solubilized or dissolved in water. But an aqueous solution, right, is a homogeneous mixture. So it's completely mixed. It's homogeneous. But when we have ionic compounds dissolved in water, they usually dissociate into their component ions. So you can form an aqueous solution from sodium chloride by stirring table salt in a glass of water. And the salt seems to disappear, but you can tell it's still there by tasting the water. All right, so when we dissolve our sodium chloride, or salt, it actually splits up like this, and we get these individual ions that float around in the solution, right? So these are chlorines, and these are sodiums. And they'll evenly disperse throughout the solution. So these substances that completely dissociate into ions in solution, they're called strong electrolytes. This is also important. This is an experiment that you can do at home. I've actually never done it myself. I don't have a 9-volt battery right now, but you could take a 9-volt battery and put it into salt water. And if you put it into pure water, nothing happens because pure water doesn't conduct electricity because water is just H2O and has no charge, right? So electricity is a flow of electrons. So if you want those electrons to flow through water, you need something like sodium chloride or a strong electrolyte. And those Na plus and Cl minus ions will actually ferry electrons through the solution. And if you do it right, you can put a 9-volt battery into a cup of water, and at one of the terminals, you'll get oxygen formed, and at the other terminal, you'll get hydrogen formed. But the important thing to know here is that electrolytes then can conduct electricity through water. Actually, the other way that this is used is to test your water purity. You can get, they're called total dissolved solids meters. And essentially what they do is they've got 2 electrodes and they've been calibrated so that when you stick them into your water, the amount of electricity that gets passed between those 2 electrodes tells you how many dissolved ions you have in your drinking water. Another example of this is something like silver nitrate. So nitrate, right, we have another one of these polyatomic anions. And when this dissolves in water, you don't get nitrogens and oxygens floating away from each other, but you keep your polyatomic anion as a group, and that separates then from your silver plus. And so they'll be floating around in the water in the solution separately from each other, but the nitrate sticks together. Not all ionic compounds, however, are soluble in water. So something like silver chloride is insoluble. So it does not dissolve. So if you get silver chloride in water, it stays as a block of silver chloride, and those ions do not dissociate into the water. Which brings us to solubility. So a compound is soluble in a particular liquid if it dissolves. A compound is insoluble if it does not dissolve in the liquid. For ionic compounds, empirical rules of solubility have been deduced from observations of many compounds. So we just have a table. I have prepared that here. So we have a table then of solubility rules. And this is the table from the book that I was talking about, right? 7.2. So this is really something you kind of just have to memorize. I would memorize them in groups, right? So we have I should make this somehow so I can write on it. We have lithium, sodium, potassium, and ammonium, and those are soluble. With any of the compounds that we're going to see in this class, those are soluble. If you get nitrate or acetate, right, the C2H3O2, also soluble. So you can remember that whole block as anything that those cations or anions form compounds with is going to be soluble. And then you just have to remember the rest of the exceptions. But we'll do some of these. All right, so here's that table again. So is each compound soluble or insoluble? So you first have to identify on the table, right, what we're looking for. So we can look for copper on our table. And I would start by looking on the left side, right? So copper, not in lithium, sodium, potassium, ammonium, not a nitrate or acetate, chlorine, bromine, iodine, sulfate. Go down the list here and you don't find copper. So, and really you can speed things up a little bit here by saying, copper is going to be a cation because it's a metal. And the only cations that we have on this list are at the very top left with lithium, sodium, potassium, and ammonium, right? So if it's not one of those, then we'll move on to our cation, or anion, excuse me. So sulfur is our anion. Right, because it's going to be copper 2 plus, sulfur 2 minus. We know it's copper 2 plus because the sulfur is 2 minus. So then we can find S2 minus, sulfur, on our table here. And we see that, so sulfur is in that second half. When either of these ions pairs with lithium, sodium, potassium, or ammonium, the compound is soluble, right? Because at the top half, there's no exceptions for those. But when it pairs with, and then also when it pairs with calcium, strontium, or barium, those are the rest of the 2A column, right? So sodium is 2A, sodium's 1A. So lithium, sodium, potassium are all 1A metals, right? Alkali metals. Calcium, strontium, barium are all three 2A or alkali earth metals, alkaline earth, right? So just trying to help you group these up in your mind. But because we don't see copper in this list of exceptions for sulfur, then the compounds containing the following ions are mostly insoluble. So we would write down that this is insoluble. Now we can look at iron. Again, we can check really quick that lithium, or our only cations that we have rules for, are lithium, sodium, potassium, and ammonium. So iron's not on there, so we're looking at sulfate. And we can find sulfate in the group of compounds containing in the mostly soluble group. But when sulfate pairs with calcium, strontium, barium, or lead, the compound is insoluble. But since we're combining sulfate with iron, we'll say that this is soluble. Now if we move on to lead carbonate, again, check our cations for lead. It's not there, but we're mixing with carbonate. And carbonate we find at the bottom in our mostly insoluble group. And the only exceptions for those, again, are lithium, sodium, potassium, and ammonium. So anything else is going to be insoluble. So, right, lead's not part of that list, so lead is insoluble. Now we have ammonium chloride. Again, we can check our cations real quick, and we see that we have ammonium, and we see that there are no exceptions for ammonium. So it's soluble. Any questions about that? I know that one. Solubility is what I always struggled the most with. But it's because I never took the time to learn it or to group them. Actually, here, I have the periodic table. Right, so we can see... Actually, let me go back to the solubility table. And I can make this just a little bit smaller. Although it's not easy to see as it is. Let's do this periodic table. Technical difficulties, please hold. Okay, right, so we have, just looking at this again, lithium, sodium, and potassium, right, are both in group 1A. Those are all soluble. And then we can also look over to, not including these, but chlorine, bromine, iodine. That's a trend on the table. Those are over in 17 here, or 7A, right? Chlorine, bromine, iodine. Those are going to be mostly soluble, unless they're mixed with silver and mercury, which are also next to each other on the periodic table. Lead then is kind of the exception. It's over to the right. It's number 82. But so it can help to go and look at where all of these things are grouped together on the periodic table, because that can help to group it in your mind. Okay. So let's move on then. When we have one of these insoluble compounds, like sodium carbonate and laundry detergent reacting with dissolved magnesium or calcium to form solids that precipitate. These reactions are examples of precipitation reactions. So reactions that form solids. And that solid is called a precipitate. And that's upon mixing two aqueous solutions. So this is a beautiful example of when you have potassium iodide mixed with lead nitrate, you get a brilliant yellow precipitate of lead iodide. Like I said, sometimes you mix two things together, they'll be cloudy for a little bit. This is giving you cloudiness, actually a complete opaqueness, and a color change. Very indicative of reaction, right? And that lead iodide is going to persist. It'll probably settle to the bottom eventually because it's insoluble, but it's persistent. So precipitation reactions do not always occur when mixing two aqueous solutions, right? So we can mix something like potassium iodide and sodium chloride. If I pull up the solubility rules again, we can see that potassium and sodium are both part of our mostly soluble with no exceptions. So we're not going to be forming any precipitates there. They just mix. And then you have ions floating around together in the solution. So the key to predicting if it's going to be a precipitation reaction is understanding that only insoluble compounds form precipitates. Right? So only the ones, again, on this table are going to be your precipitates. Whoops. So we have two solutions containing soluble compounds. They combine and an insoluble compound precipitates out. So what happens when we mix potassium iodide and lead nitrate? So before we mix them, right, we've got these free ions floating around. And if we pull up our solubility table, we can find iodide. And if iodide mixes with lead, the compound is insoluble. So we can predict that when we mix these together, they might not... sometimes it doesn't happen immediately. This was another question that was tricky on the lab, that when you mixed, I think it was the barium sulfate solution, you could dissolve the barium sulfate, or no, it was barium sulfate was a solid. You could mix the barium chloride or whatever it was. It dissolves, and the dissolution, the dissolving of the barium, whatever the powder was, that is a physical process. The precipitate forms later after it's dissolved. So immediately after mixing, when we do one of these reactions, though, we want to look at what are our combinations. So we have, what are our possible combinations of ions? So we already have that potassium iodide and lead nitrate are both aqueous. So we actually can ignore those combinations. And what we'll do is we'll take the anions and we will swap them. So we'll get lead iodide, and we'll get potassium nitrate. So then we will check these new products to see if they are soluble or insoluble. Right? And so like we saw from the solubility table, lead iodide precipitates, clumps up, and forms a solid. But the potassium and the nitrate ions remain in solution. So they continue to float around. They're not forming any solids. So when we write equations for precipitation reactions, we do the formulas of the two compounds being mixed as reactants in a chemical equation. Below the equation, then, we want to write the formulas of the ions. Right? So write out all the ions with their charges. Then we'll exchange the anions and rewrite the ion formulas below the product side. All right, that's what I was saying. We don't need to check our reactants. We know those are soluble. Then we use our solubility rules to determine if either of the new pairs of ions is insoluble. If both pairs are soluble, then you write no reaction where you would have written the products. If one or both of the new ion pairs is insoluble, you write the formulas of the compounds after the arrow. You use aqueous to indicate a soluble product, and S for solid to indicate an insoluble product. And then you balance the equation by adding coefficients as needed. But again, do not change subscripts. You never change subscripts. Okay. So we're going to look at potassium hydroxide and nickel bromide. So let's write out then, right, our reactants. We know what those are going to be. Potassium, and then hydroxide is OH, aqueous. Leave a little space, and then we'll do nickel. And we know it's nickel 2. Bromide again is in the 7A. So it's a 1 minus charge. Okay, now we have to predict what our products are going to be. So we'll write down all of our ions. Oops, sorry. So we drop these into solution. They split up, right? Potassium, hydroxide. We're going to get nickel 2 plus, right? And then Br minus. So now what we'll do is these guys will remain fixed. And we will flip-flop these. So that our possible products are potassium bromide and nickel. Right, we can just balance the charges real quick. Nickel hydroxide. So now, are these going to be soluble or insoluble? Pull up our solubility table. And we look at potassium, again, as one of our mostly soluble with no exceptions. So we can move on to nickel, which isn't part of those cations. So then we'll move to we could do bromine too. So when bromine pairs with silver, mercury, or lead, we don't have any of those. Then we can do our hydroxide. And we have hydroxide as mostly insoluble. And then we just need to check the exceptions. So when either of these ions pairs with lithium, sodium, potassium, or ammonium, soluble, but we're not mixing with those. We're mixing with nickel. Then our other exception for hydroxide is when hydroxide pairs with calcium, strontium, or barium, the compound is slightly soluble. So for the purposes of this, unless I'm asking you, is it slightly soluble? write that it is insoluble. So we're mixing, hydroxide and nickel. Nickel's not part of those exceptions, so that's going to be our solid. So we know we have a reaction because we have something that is insoluble. So then again, leave space for a coefficient, potassium bromine, all right, with charges balanced, plus nickel, hydroxide. Oh, and I forgot to, this is aqueous, and now this is solid. And now we can go back and balance. So we can start with, because we have everything flip-flopping, you can really start anywhere. According to the rules of the book, you start with the metals, I guess. But let's just start with, we can check potassium. We have one potassium on either side. Move to hydroxide. We have one hydroxide on the left. We have two hydroxides on the right. So I'll add a 2 coefficient on the left to make that match. Now we've changed the number of potassiums. So we can move to the right side and see, okay, we have one potassium on the right, one on the left, or 2 on the left. So we add a coefficient here, which changes the number of bromine. Then we check bromine on the left. And this is how you can see, this is how I do these problems, is I will pick one that needs to be changed, and I will change it, and then I will see if that changes anything there. If it changes anything else, then I'll move to wherever that needs to be corrected, and you kind of just move from one thing to the next, changing as you go to make things match. So now we have 2 bromines on the right, 1 bromine on the left. We can see I have 1 nickel on the left and 1 nickel on the right. So we've balanced our chemical equation. And we know that nickel hydroxide is our solid. Okay. Is there another example? 2 more examples? Okay. I'll do these 2 more examples and then we'll take a break. So let's write an equation for the precipitation reaction that occurs, if any, when we mix ammonium chloride into iron nitrate. So, ammonium, NH4, and then chlorine. Oh, again, aqueous, plus iron nitrate. And we see it's iron 3. So you can guess how many nitrates we're going to use, or you should know how many nitrates we're going to use. And then we will write out our ions. So we'll get NH4 plus, and we'll do Cl minus, and we have iron 3 plus, and we have nitrate. Because we're just using this to do this flip-flop and see what our products are going to be, we don't need to write down the correct number here or anything. We just want to know what our new combinations are going to be. So I'm going to put these in boxes. They're going to stay. And we're going to flip-flop our anions. So we'll get ammonium nitrate. And then we will also get iron chloride. And I'm just balancing these charges as I go for when we move them up into our products if they end up being insoluble. So now we can check ammonia. We do find on our list as one without exceptions, right? Mostly soluble without exceptions. So that is going to be soluble. I suppose you could mark that here, right? We could write aqueous because it's not going to be a solid. And then we can do iron. Iron is not on our list. Chlorine is. When any of these, so if we look at chlorine in the 3rd row on the mostly soluble compounds, when any of these ions pair with silver, mercury, or lead, the compound is insoluble. And because we're mixing with iron, this is actually going to be soluble. So we can say that this is aqueous as well. Now, because both of these are soluble, we write no reaction.
Where's the, I'm not spotting the iron part, so when it, chlorine in the iron part, where's the iron? I don't see where it shows that that's soluble. Am I just
Right,
blind?
because it's not on the list is actually why. So if you look at chlorine, right, so we have chlorine, and then to the right of that, it says when any of these ions pair with silver, mercury, or lead, the compound is insoluble. So those combinations would not be soluble. For everything else, a chlorine as a part of a molecule would be soluble.
Oh, okay.
Yeah, so any other cation, it's soluble. And then I'm just checking too that for the cations, right? Because this list only has cations at the very top, and there's only 4 of them. There are, in these exceptions, there are other cations. And if you notice, those are the same most of the time. Calcium, strontium, barium. And then down in our mostly soluble, those are calcium, strontium, barium, calcium, strontium, barium. So in terms of the ones, basically need to remember these as exclusive lists. So you can say if it's hydroxide or sulfur, if it's mixed with anything else other than calcium, strontium, or barium, it's going to be insoluble. Those will precipitate. And the reverse is true for sulfate. Sorry. I said that backwards. If it's calcium, strontium, or barium combined with oxygen or sulfate, those are soluble. Anything else is insoluble. For sulfate, everything is soluble unless it's calcium, strontium, barium, or lead, and those are insoluble. It is confusing, I know. Because there's a lot of, well, it's this most of the time, but then it's that some of the time, and it's this most of the time, but it's that some of the time. And that is, unfortunately, just how it is. Okay, so one more. We have potassium sulfate and strontium nitrate. So we just write these out, right? Potassium. So we know sulfate is SO4 2-, so we know we're going to need 2 potassiums. And strontium nitrate, so SR, strontium is a 2+ charge. So we're going to do, not NO4, NO3 for nitrate, and we're going to have 2 of those. And again, we're going to write down all of our possible ions here, or all of the ions in the solution with their charges. And then NO3-. We're not swapping strontium, and we're not swapping potassium, but we're swapping the nitrate and the sulfate. So we're going to get potassium nitrate, and we're going to get strontium sulfate, right? And since these both have strontium and sulfate, both have strontium with a 2+, sulfate with a 2-, right? Those mix 1-to-1. And now we'll go to our solubility table, and we can see if we start with potassium. Potassium is one of those always soluble cations. Nitrate is also always soluble. And then strontium is in our list of exceptions, but we have to look at what it's mixed with, and it's mixed with sulfate. So if we combine sulfate, and then it says when sulfate is mostly soluble, except when sulfate pairs with calcium, strontium, barium, or lead. The compound is insoluble. So we know that this will be our solid, because strontium is in the list of exceptions. So then I'll do potassium nitrate. Like I said, I have been bad about these again. Aqueous. Oops, did those backwards. Plus space for coefficient. SR SO4 solid. So then again, to balance these, I'm going to start with, right, so you can really start with either of these that we have two of on the left and one of on the right. I'm going to start with potassium. Let's see, we have two potassiums on the left. We have one potassium on the right. And so then we will add a 2 coefficient there. So now we have two potassiums. We have two nitrates now. So let's check on the left side. And on the left side, we have two nitrates. And just to round it out and check everything, strontium, we have one strontium on the left, one on the right. We have one sulfate on the right, one sulfate on the left. So we've successfully balanced it. Okay. Let's take a short 5-minute break here. Let's come back at 11. Let's do 11:24. 11:24. I'll come back.
While everybody's taking a break, can you just help me real quick with just a
sure.
balancing thing? So we have gaseous ammonia reacting with gaseous oxygen. So that would be, so gaseous ammonia is NH3, right? And then plus gaseous oxygen, that's O2.
Yeah.
Right. So NH3 plus O2. And then that forms nitrogen monoxide, that's NO. And then gaseous water. So that's just H2O, right?
H2O. Yeah.
For some reason I'm like banging my head here. I can't balance. You do it after if it.
So you've got NH3.
Okay. NH3 plus O2. And that makes NO plus H2O.
I think it's fine because it's, we'll just do it right now because this is what we've been talking about.
Yeah, that's what I mean. It's
Yeah. So again, you want to, we'll end with oxygen here, right? Because we have oxygen by itself. And that's easy to work with. I would just start with the hydrogens then. That's the only thing that needs to be balanced at the moment, right? Because we have 3 on the left, 2 on the right. We have 1 nitrogen on the left, 1 nitrogen on the right. So then, again, this is one of those things. If you end up with a 2 and a 3, you can use that crisscross rule. So we'll add a 2 coefficient here and a 3 there. Because now we have 6 hydrogens and 6 hydrogens. Now we have 3 oxygens. We also have, well, we'll end with oxygen, right? So we have 2 nitrogens. And so we'll just do, to make that match on the right, we'll do 2 NO.
Yeah.
So then if we reassess here, we've got 2 nitrogens, 6 hydrogens, and then 2 oxygens. And then we've got 2 nitrogens, 6 hydrogens, and we have 3
oxygen.
3 oxygens.
That's
right.
Where
so then this is like we did before. Or let me see. We'll do it in that pink again, right? So we do, since we have O2, we need to do 3 oxygens divided by 2 because of this O2.
Yep.
So we'll get 1.5.
Yeah.
And that kind of makes sense too, right? If you have 1.5 O2s, that's 3. So put 1.5 in there, which then tells us that we need to multiply everything by 2. So then we'll get 4 NH3 gas plus 3 O2 gas, 4 NO gas, and 6 H2O gas. I'm assuming those last two are gases.
Yeah. Okay, and then we assessed. We got
Yep.
4 nitrogen, 12. Yep, 12 hydrogen.
Yep. Oh,
Okay,
sorry.
so,
4 and
there's
6.
another, huh? Oh wait, no, we have 7 oxygen. Or wait a second here. We have,
What happened? What did I do?
yeah. See, so this is where, okay, so because now on the left we have 6 oxygens, and then on the right we have 4 plus 6. We have 10 oxygens.
Oh, it's because I counted wrong. It's because we don't have 3. I forgot to multiply, right? So we have 5. We have 5 oxygens on the right. Before we multiplied, we had 5. So we need to divide that by 2, which gives us 2.5. So this should be 2.5. And then when we multiply everything by 2 still, now we have 5.
Okay.
That's my bad.
So that was exactly what I kept missing. I missed that also. So you missed the oxygens on that NO, right? Okay, that's
I
what I
missed
kept doing, and I was like, man, is the book wrong or something?
Yeah,
Okay.
so I missed the oxygens on the or I missed the coefficient on the water to multiply by the oxygens to get the right number of oxygens.
Okay, I was doing the exact same thing wrong, so that's funny.
Yeah, I got
But
to make sure you count them all.
cool. Okay.
All right. Well, it's
All right.
11:24 now, but I do have to go to the bathroom, so
Yeah.
um, be just a minute, and then we'll get back into it. Turn my. We'll just do this. Okay. Da-da-da-da-da-da-da-da. I need to get one of those. This is what I want. Stream decks. Stream deck. All right. So continuing on with ionic solutions, when we write a molecular equation, that shows the complete neutral formula for every compound in the reaction. We can also write a complete ionic equation, which shows the aqueous ionic compounds as ions. And when we write the complete ionic equations, you separate only the aqueous ionic compounds into their constituent ions. You do not separate solid, liquid, or gas compounds. So just aqueous. Sometimes we have these things, they're called spectator ions. Ions in the complete ionic equation that are unchanged on both sides. And so we can often simplify our equations and show more clearly what is happening by omitting those spectator ions. And then the result of omitting those spectator ions is the net ionic equation, which shows only the species that actually participate in the reaction. And here species means a kind or sort of thing, which would be here all the different molecules and ions. So we're showing only the molecules and ions that participate in the reaction in a net ionic equation. Right, so summarizing here again, molecular equation is the complete neutral formulas for every compound in the reaction. We balance that. A complete ionic equation shows all of the species as they are actually present in solution. And a net ionic equation shows only the species that actually participate in the reaction. So we'll see some examples of that. So looking at this equation, right, we have aqueous, we have a liquid, water's a liquid, and aqueous. So when we write we'll write a complete ionic equation and a net ionic equation. So first, what we're going to do is we're going to separate out our ions. Right, so we have 2H plus Br minus, and this is already balanced, so we don't really need to leave spaces for coefficients. We have calcium 2 plus.
2Br, right?
Sorry, 2Br. Yep, thank you. Plus 2OH minus, and that's going to go to 2H2O, right? Because water is a liquid here. Feels a little bit silly to say, but water is a liquid. And so then we can leave that as it is. And then we'll have calcium 2 plus 2 Br minus. Because this is an aqueous solution, it's 2 Br minus. Okay, so now that we have this, we have our complete ionic equation written out here. So this is
I'm sorry,
complete.
why isn't it 1Br? Don't you do the crisscross?
Sorry, 1Br?
Yeah, why on the end there? Why isn't it calcium and just regular Br? Don't you do the crisscross?
Mostly, well, it's because we've got ions here. So it's 2 Br instead of 1 Br2. Because this doesn't exist as Br2 in solution.
Oh, okay.
And you'll see too that matches with the
Yeah, it matches with the left side. Okay, sorry, go ahead.
Yeah.
You
would keep it as Br if for some reason, and this is not I don't know if this is relevant for ionic equations like this. If you somehow evolved bromine gas, so if you had, and then this applies, the rule applies from before, right? So if we have Br2 gas, since it's a gas, we don't break it into its constituent ions, just like we don't for liquids or solids. Okay, so right, so this is our complete ionic equation. And now what we do is we find which ions do not participate in the reaction. So we look on the left side and the right side, we see we have Br minus, stays as Br minus on both sides. We also have calcium 2 plus, which stays as calcium 2 plus on either side of the reaction. So we can eliminate those and ignore them because they're just hanging around. They're spectators. They're just watching the reaction take place. So then we can have 2H plus 2OH minus makes 2H2O. Again, liquid. So we can remove these coefficients actually, because it's balanced. And for our net ionic equation, we want the simplest form. So H2O is, or sorry, our hydride ion is combining with hydroxide to form water. And so then this is our net ionic. All right, so now that we've talked about ionic equations, we can talk about acid-base neutralization reactions. Acids tend to form these H plus hydride ions in solution. They're easily recognized because their formulas begin with hydrogen, right? So we talked about how we name acids. So from this previous example, right, HBr is hydrobromic acid. So you're not going to taste any of them, but acids have a sour taste, and they can dissolve some metals. Bases, on the other hand, tend to form hydroxide ions, right? So, or OH minus. They'll form metal hydroxides. They taste bitter, and they feel slippery, right? So soaps often have bases in them, and that's why soap is slippery. So in our acid-base neutralization reactions, we have just a list of some common acids and bases, right? Hydrochloric acid, hydrobromic acid, sodium hydroxide, lithium hydroxide, right? The bases we name according to like our oxyanions, right? So hydroxide is an oxyanion. So calcium hydroxide, barium hydroxide, and then the acids, right, are named according to the acid rules. So then we also have things like nitric acid, sulfuric, and then perchloric acid, right? Because chlorate would be ClO3, and acetic acid. And in these acid-base reactions, also called neutralization reactions, we're forming water upon mixing an acid and a base, right? So we have our hydroxide or hydride, H plus. We have our OH minus, and those are combining to form water. And then the other product in these ionic or in these neutralization reactions is an ionic compound called a salt. In this case, it's NaCl table salt, but it's can be any ionic compound, and that usually remains dissolved in the solution. An example of an assault rifle. So the pattern of acid-base reactions is acid plus base equals water and salt. That's pretty much acid-base. All acid-base reactions are going to be some form of that. The net ionic equation for many acid-base reactions is the same, right? So we're mixing hydride with hydroxide, and we're getting water. Because the part of the acid and part of the base is going to be combining to make the salt. And then if the salt is aqueous, it remains as its constituent ions. It remains as its separate ions in the solution, and so is a spectator. So let's look at H2SO4. So we want to write a molecular and a net ionic equation here. So H2SO4 plus, and since we're going to be balancing this, potassium hydroxide, right? We want these space for coefficients. I'm going to move this up. Right, and so one of our things, because this is an acid-base reaction, because we have sulfuric acid, potassium hydroxide, we know one of our products is going to be water, and then our other product is going to be the combination of potassium, it'll be potassium 2 because sulfate is SO4, and then we'll balance this. And here it's easier to start with the two portions that don't become water. So we'll do potassium first. So do 2 potassiums there. That gives us 2 hydroxides. So now we have 2 oxygens. And so we'll balance this. That'll be 2. All right, so now we have 4 hydrogens. Oh, this might be an example of where we start getting into a loop. Did I do this? Right. Okay. So we've gotten. Let's just play this out. Let's see what happens. So we got 2 potassiums here. So I put 2 over here as the coefficient. Now we have 2 potassiums. But that gives us 2 oxygens, 2 hydrogens. Right, and sulfate's going to stay as a combined polyatomic anion or oxyanion. So now we've got 3 hydrogens, and we have 2 oxygens.
There's 4 hydrogens.
4 hydrogens.
That's
Thank you.
balanced.
Yes, it is balanced. Thank you. Again, forgetting to count the other hydrogens. All of the hydrogens in the solution. So make sure you're counting all of them. Okay, so we've got our balanced molecular equation. Now we can write this out as the constituent ions, right? So we have 2 hydrogens. Yeah, and then we want a net ionic equation, but we'll go through the... wait. I gotta remind myself on the names here. Because there's a complete ionic equation. Right, so we'll do the complete ionic equation and then make the net ionic equation from that. So do SO4 2 minus plus 2 potassiums plus 2 hydroxides. Right, and then water is a liquid. Water is always a liquid. So we'll have 2 H2O plus 2 K plus SO4 2 minus. So again, we just check on the left and right to see what still exists on the left and the right side. And we're going to see that we have potassium and we have sulfate. So our resulting reaction is going to be 2H plus 2OH minus makes 2H2O. And that would be our net ionic equation. Well, minus the coefficients, right? Write that down. Right, and just like we saw in our examples or when we were learning about these, we can see that, yeah, we do in fact get this exact same net ionic equation for this acid-base neutralization reaction. So gas, moving on then from our acids and bases, which are essentially, right, they're ionic. Moving on to gas evolution reactions. There's a small set of molecules that you should be on the lookout for that evolve into gases. I believe there's a table. So some aqueous reactions form gases as a product, and these are called gas evolution reactions. Some form this gas directly. So if we mix H2SO4 plus lithium sulfide, we get hydrogen sulfide. And hydrogen sulfide is a gas. So if you get hydrogen sulfide, as a product, that's a gas. And you know it's a gas evolution reaction. There are some other ones. So carbonate forms an intermediate first. So you go from, in this reaction, HCl plus sodium bicarbonate gives us carbonate. That carbonate then decomposes into H2O and CO2. And so that's going to be another type of gas evolution reaction. Good, okay, there is a table. So sulfides, H2S, is going to be a gas. Carbonates and bicarbonates will form CO2 as a gas. And H2O, right? So we get H2O along with those. Sulfites and bisulfites, similar thing. We're going to get SO2 gas, but we're also going to get water and SO2 gas. And then ammonium. So this ammonium hydroxide will form ammonia gas. Right, so ammonia is the gas. That's this NH3. The one with a charge, the version of ammonium, is ammonium. Right? Also written over here. So these are the ones that you need to memorize as those are the gas evolving compounds. So sulfides form gases directly. Carbonates, sulfites, and ammonium all form them as an intermediate product. Or they form an intermediate product first and then a gas. So we write down our equations for gas evolution reactions. We want to write a skeletal equation first that includes the reactants and the products that form when the cation of each reactant combines with the anion of the other. And recognize that H2CO3, H2SO3, NH4OH will decompose then. So you'll have another step after your products. There will be another reaction there to form water and CO2, SO2, and ammonia, respectively. And then you'll write that corresponding reaction and then balance the whole thing. So let's mix some hydrobromic acid, all right, HBr, and aqueous potassium sulfite. So we're writing down now our skeletal equation. And again, we're going to swap these. So we're going to get, so we're going to get H2SO3 plus potassium bromide. We know H2SO3 is one of our gas evolving compounds. So we're going to write another step here. And this is going to go from H2SO3 to H2O, liquid, plus SO2 gas. And now, after identifying that this is, right, from our previous here, a sulfite and bisulfites, so we have our sulfite here, we can now balance the whole thing. So,
Where did the KBr go? So should that KBr follow the H2O and the SO2 also?
I think actually, I mean, the way I've done this in the past is I write it this way. So I would write it like this and then do H2O down here and then SO2, or not another one of those, a plus. Plus SO2. So I don't think, I mean, you can write the KBr over here. Yeah. Right, and it just stays potassium bromide. Or if you're typing it, obviously you're not going to be able to do something like this. Yeah, so let's do it this way. So then, yeah, now you can balance all the way across. Right, and so that we can see we have two potassiums on the left. We have one bromine throughout. We're going to need two hydrogens. So we do two hydrogens. Now we have two bromines. So we can go to the middle and say we have two potassium bromides. And then following that to go to the very end, two. Right, so then the KBr is balanced. We now have our two hydrogens. We have one sulfite. Sorry, I should be like... So sulfite is one sulfite. And then, this is where it gets a little bit tricky, right? But this H2SO3 is becoming the H2O and the SO2 gas. So if we count these count these together, right? We have two hydrogens, one sulfur, and then three oxygens. So we end up with our balanced equation.
balance all three parts there. We can't just cut out the middle part since it transferred into the third part.
No. Yeah, because it's an intermediate. I want you to show that intermediate step. Because you are forming the sulfite, but then it's becoming, right, it goes on another step. This is so oxidation reduction reactions. We'll talk more about these tomorrow because there is some other stuff that you do need to know about them. And these are reactions that involve the transfer of electrons. And so we call, so there's a way to remember it. It's on the next page. But we're transferring electrons. Redox reactions are responsible for things like rusting of iron, bleaching of hair, and the production of electricity, actually, in batteries. Transferring those electrons then out into extra electrons, really, and using those electrons to power things. But many but not all redox reactions involve the reaction of a substance with oxygen. So we have a few examples here. We have like hydrogen combining with oxygen to form water, which is the reaction that powers the space shuttle. It's rocket fuel. We also have rusting of iron, right? We have iron combining with oxygen to form iron oxide. And when we combust when you burn anything, you're adding oxygen to it to form, at least in terms of hydrocarbons, so natural gas, you're forming CO2 and water. So redox reactions, they might not involve oxygen. So when we're not using oxygen, like here, we have sodium and chlorine combining to make sodium chloride. And a fundamental definition of oxidation is the loss of electrons, whereas the definition of reduction is the gain of electrons. And this is the acronym that I like to use, oil rig. Oxidation is loss, reduction is gain. So when we lose electrons, it's being oxidized. And when it's gaining electrons, it's being reduced. So oxidation and reduction must occur together. So something will always be oxidized, and there will also be something else that's being reduced, and that's the transfer of your electrons. From the thing being oxidized, oxidation is lost, to the thing being reduced, reduction is gain. So for now, you just need to be able to identify redox reactions. So
From that previous example, how we identify it is you're losing the subscript of that chlorine.
So actually, the way you identify it here, right? So here, sodium doesn't have a charge. It's just elemental sodium. But if you look over here at sodium chloride, we've combined these together. So actually, sodium now has a positive charge, and chlorine has a minus charge, right? Because here also, I'll just put NC, right? No charge, no charge. So what's happening is
why does
you're
it have
taking
a charge? I thought because in group 1A, it's got a positive plus charge.
So the compounds in group, or the elements in group 1A, form +1 ions. They're not always +1 ions. But that's why here we go from elemental sodium to Na+, because it wants to lose that one electron, whereas chlorine is in 7A, so it wants to gain one more electron to have a 1 minus charge. Does that make sense?
No, but we can continue.
So, I mean, if you look at it here too, it's just written as sodium. It would have to have a charge if it had a charge. Same for chlorine. If chlorine was written here, because in our molecular equations, everything has balanced charges. So everything has a charge of 0 because it's combined with something else that balances that charge. And if it's by itself, then it must have a charge of 0.
Oh, okay. So if
Right,
you
so
just see O2 out there by itself, then that's
zero charge.
for sure. Okay.
So
Cool.
that's why, and we are going to go over these more. But so okay, let's do this. Let's go over here then, since we're on this topic. Looking at this bottom problem, right? We have carbon. This is getting into oxidation numbers, which we will talk about tomorrow. So we have carbon here by itself, right? So it must have a zero charge. Oxygen by itself has a zero charge. And again, this is getting into oxidation numbers. But for CO2, when we combine these, they're bound together, right? So they have charges. And actually, if you look at, what is the periodic table? Right, so carbon is in
Minus
4A,
+4, yeah.
right? It's going to be a +4 charge. So CO2 here is going to be C4 plus, and then our oxygen, so this, again, oxidation numbers, but oxygen only forms a 2 minus charge. So we have 2 oxygens, atoms, each with a 2 minus charge. So then we have this 4 plus 4 minus, and those charges balance.
That's not a redox reaction right there.
This is a redox reaction, right? Because we went from 0 charge on carbon, 0 charge on oxygen, to a +4 charge and a -2 charge on oxygen, or +4 on carbon, -2 on oxygen. So it's a redox.
Okay.
The simpler rules are back here. So if a substance reacts with elemental oxygen, right, that's O2 with a 0 charge. If a metal reacts with a non-metal, those will form. So and that, again, that's like we had previously, right? Sodium, 0 charge, plus chlorine, Cl2, because it's a Brinkelhoff, but 0 charge. We now have a metal reacting with a non-metal. And then also,
makes it more sense.
sorry, say that again?
That list makes it more sense. I understand it better with that list there.
Yeah, because we haven't talked about the other stuff. But we will tomorrow morning. That's what we're going to talk about first tomorrow morning. So
Cool.
you can let that ruminate. Think about it a little more. Read ahead. Actually, so we're going to cover a little bit out of chapter 16 tomorrow. Is where that oxidation reduction stuff is. Okay, so now looking at these. Oh, and then just to restate, right? So one substance transfer electrons to another substance. So which of these are redox reactions? So for A, right, we have lithium, which is a metal. That's in 1A. And we have chlorine, which is a nonmetal. And again, both of these, 0 charge, right? Because it's a molecular equation, they have to have 0 charge.
So, non-metal.
Yep, nonmetal with a metal.
Okay.
So that's that's an oxidation, or redox. We use redox as a combination of oxidation and reduction. So those are redox reactions. On this next one, so this would be an ionic equation, and probably a net ionic equation, because we have charges. So because charges are present, and the charges are present here to highlight to us that, so we have aluminum, 0 charge. It goes from 0 to +3. So we're losing electrons there. And then we have tin, which goes from 2 plus, to 0 charge. All right, tin goes from +2 to 0, so it's gaining electrons, right? Because every electron has a 1 minus charge. And so to cancel out that 2 plus, we add 2 electrons. And because we have an exchange of electrons going on, that's a redox. This next one, we have lead nitrate and we have lithium chloride. So We don't have anything reacting with elemental oxygen. We don't have... I guess we have a metal, but not an elemental metal reacting with a non-metal. Because we can look here, and if we determine what the charges are, we know nitrate has a -1 charge, right? There's 2 of those. So that gives us -2. Or sorry. Yeah, -2. So we know that lead here has a +2. And if we just track lead over to the right side, chlorine is in 7A, so it's also a -1 charge. And there's 2 of them. So again, we have a -2. And so lead here is still +2. And if we look at lithium, it's the same thing, right? So we have 1 chlorine, that's a 1- charge. So lithium, you could also look at lithium being in group 1A. Lithium has a plus charge. And this lithium on the right side, again, nitrate is a -1. So lithium is plus. So nothing has changed its charge. So we have no exchange of electrons. So this is not redox. And then we've already talked about this last one, but also we're reacting with elemental oxygen, which is one of our simple rules. Good enough? It's actually been taking quite as long as I thought it would. So we can go and do some of the even problems from the back of the book. So combustion reactions then are a subtype of oxidation reduction or redox reactions, characterized by the reaction of a substance, again with elemental oxygen, one of our redox simple rules, to form one or more oxygen-containing compounds, often including water. Combustion reactions are exothermic, right? If you've burned things before, you know they're exothermic. And then compounds containing carbon and hydrogen, or carbon, hydrogen, and oxygen, always form carbon dioxide and water upon combustion. So here's an example of a combustion reaction. So we have ethanol from alcoholic beverages, combusts to form carbon dioxide and water. So we have our C2H5OH, which is ethanol, combining with elemental oxygen, right? Again, 0 charge here. And that forms our CO2 and water. Similarly, octane in gasoline reacts with oxygen to form carbon dioxide and water. Right? So again, elemental oxygen, 0 charge. And then that forms CO2 and water again. Different quantities, right? So you have to balance these. But if you only have carbon and hydrogen and oxygen in whatever is being combined with oxygen, you'll end up with CO2 and water. Okay, so let's write a balanced equation for the combustion of liquid pentane, which is a component of gasoline. So C5H12, right? And we're combusting, so it means we're combining it with elemental oxygen, leaving space for our coefficients. And because we only have carbon, hydrogen, and oxygen in our reaction, our combustion reaction, we're going to end up with CO2, C2O, CO2 plus water, H2O. And now we just balance. So we start with carbon. These here. Right, so we have 5 carbons on the left. We want 5 carbons on the right. We have 12 hydrogens on the left. So we're going to do 6 times H2 here in our water to get 12 of those. And now we have 10 oxygens and we have 6 oxygens. So we multiply by 8, multiply O2 by 8 to give us the appropriate number of oxygens. I realize that this looks like I wrote 160. If I put a semicolon in between, or if I do so there's a combustion reaction. So again, right, everything that we do, or everything we've done so far really in chemistry, comes down to these sort of decision trees of trying to classify the things that are happening. So out of chemical reactions, we now have precipitation reactions, acid-base reactions, gas evolution reactions, and as noted here, many gas evolution reactions are also acid-base reactions, but not all of them. And then we have oxidation reduction reactions. Within that, we have combustion. All right, so we can talk about precipitation forms a solid. Acid-base reactions form water. Gas evolution reactions, right, a little bit less clear, but you're always going to have, I believe it was CO, right, carbonate, or H2SO3, sulfite, sulfurous acid, or the gas that another gas you can evolve is H2S. I feel like there was one more there, but you can go back and look that up, right? So in this column, we're looking for these things. And then for oxidation,
One, right?
what was the other one?
Ammonium
Ammonium.
is NO3, right?
Yeah. So if you form NH4OH, ammonium hydroxide, that will form a gas. So we're looking for those four as our gas evolution reactions. And then when we look at oxidation reduction, is it an elemental metal plus elemental, sorry, that's sloppy. I can zoom, I guess. Non-metal. Sort of one of the classifications there. Or is it combining with elemental oxygen? Or transfer of electrons? Right, so you can kind of break these down into these simple rules. There's a lot of them, and I guess I should say too that there's going to be some sort of H plus OH minus for acid base, because combustion reactions also form water. And then for combustion reactions, we're really looking at O2 plus some kind of CX, HX, right? Or we've got, or I should say Y, because those are going to be different. CXHY, right? We're combining oxygen with some hydrocarbon, meaning a combination of hydrogens and oxygens, and possibly there could be another oxygen in that hydrocarbon, like we saw with ethanol. I think the most important thing is to not just write these rules down and memorize them, or write these rules down and then use that on the exam, but to understand why these are broken down this way. And then if you understand that, then you can figure out any of them. So again, here's some more sort of like the generic sort of formula, a formula if you will. If you've got synthesis or combination, that's going to be A plus B combining to make AB.
I'm sorry, can you back up this slide just one? I was trying to write it down just real quick.
Oh, yeah.
Okay, we're good. Thank you.
Uh-huh. All right. So, okay, so we've talked about all these different types of reactions. We also have these other classifications for what is happening within a reaction. And we've sort of mentioned these, and I've mentioned these briefly, but we've got synthesis or combination reactions, where we have, molecular element A plus molecular element B combining to make AB. Decomposition is the opposite, where we're taking A and B, or we're taking AB combined and splitting it into A and B. So an example of synthesis or combination would be like our H plus OH minus to form water. An example of decomposition would be like H2SO3 would decompose into H2O plus SO2, right, as a gas. We have a displacement reaction. So displacement reaction would be really a lot of those ionic reactions that we talked about, reactions with electrolytes, where you have one thing swapping out with another to form a solid. But really it comes down to, right, A, you can see A is here, A is here, B, B, and then C, right? So you can see that we've swapped. C has gone from being combined with B to combining with A. And then the double displacement is, sort of displacement, but we've done it twice. So in this example, A and C, or B and D really, have traded places, so that we end up with A and D. And we've also combined B with C. Well, that's hard to see. What do I not have? Green. So simpler substances combining to form more complex substances, right? That's our synthesis. We're forming a single compound. So here, combining sodium with chlorine to make sodium chloride. And then decomposition is where we're taking a complex substance that decomposes into form simpler substances. Oh, this is what I was talking about, where you take a battery, 9-volt battery, and put it in water, and you're taking that water and breaking it up into hydrogen and oxygen. So one reactant, right? So synthesis or combination, we have one product. Decomposition, we have one reactant. With single displacement reactions, we're displacing one compound in another compound, or an element's displacing another in a compound. So we have zinc here taking the place of copper. Right, so we're taking our copper chloride, and we're taking the copper out, and we're putting zinc in instead. Oh. So that's your single displacement. And then double displacement would be taking two elements or groups of elements in two different compounds, and then you exchange places to form two new compounds. The kinds of reactions that may be double displacements are precipitation reactions, acid-base reactions, and gas evolution reactions, where you're forming, two new compounds. So chemical reactions, we're classifying, out of all chemical reactions, is it a synthesis, is it a decomposition, single displacement, or double displacement? So let's do some classification of our own. So for this first one, right, identify what's going on, and we can color code these to make it easier to see. Aluminum, aluminum. Do hydrogen, hydrogen. And then PO4 is a phosphate, right? So that's a polyatomic ion or oxyanion. So we can see that we've gone from the aluminum by itself to aluminum with phosphate, and now the hydrogen is actually by itself. So this would be a single displacement. Next, we have copper on the right, right? And then we have sulfate, and then sulfate not bound to copper, potassium. Now potassium and the sulfate have combined, and the copper and hydroxide are combined. Right? So we've taken these anions and we've swapped them. So we've done two displacements, or a double displacement. On this next one, we have our potassium and bromine. So potassium combining with bromine, and now we have a single product. So we've taken two things and we've made a new thing. This is synthesis. And then you could, by process of elimination, probably figure out what our last one's going to be. Right? But we have copper chloride separating. So we have one reactant and two products. Be a decomposition. That is the end of that. Are there any questions?
I have questions, but not about this.
Okay. I will, okay, so then that'll be the end of the lecture. Just remember there's a test on Friday, and any other notes? I wanted to do that extra quiz, but I don't think I'm going to have time for it. I will try to release a practice quiz for the type of question that I wanted to have there, and do that on the, there will be an example of that question on the exam. So I will get that quiz out tonight, but it won't be for a grade, it'll be a practice quiz. All right, so I'll stop the recording.